In the following lectures, we are going to start talking about thermochemistry. This is really going to be the study of energy in chemical reactions. And we just finished talking about types of chemical reactions and being able to do some predictive calculations about how much will form. And now we're going to focus on how heat will flow in and out of reactions depending on the type they are. And then this class will build into looking at the actual structure of an atom and structures of molecules. So that way we can better understand how these molecules are behaving in solutions in the chemical reactions we've started talking about. So we're going to start with an overview to kind of lay a foundation for the calculations and the concepts that we're going to present in this chapter. And I want to make sure that we all have kind of a similar take on what energy is and temperature and heat before we really start talking about these in detail. So this will be a little bit of an overview lecture. So let's start by defining energy. So energy is the capacity to supply heat or do work. And that work means that it's an action of a force across a distance, right? So work is force over a distance. And I like this picture of pushing a box because for me to think about work, I usually think about something that's hard for me to do, to visualize it. And so pushing a really heavy box across a floor, I have to impose force on that box over a distance to move it. I'm doing work. And I know that because I'm sweating and I'm expending energy. But so that's kind of the most intuitive way for me to think about it. But we're going to not be pushing boxes across rooms. We're going to be having molecules interact, right? And atoms. And so it's going to be the ability of anything to either give off heat to a system, into a system, or to apply that force over a distance to do some work. And that might be the work of a molecule imposing force over onto a glass wall of a beaker or something like that. So within energy, I'd like to break that down into the two types of energy that we have, potential energy and kinetic energy. If you've had a little bit of a physics course already before, this would hopefully be familiar. Potential energy is this idea that we have stored energy, whereas kinetic energy is the energy due to motion. And so the typical example is something that's up on a hill or on top of a table or something, and when it's raised above the ground, it has potential energy due to its position relative to the ground. And if it falls off, it'll convert that potential energy into kinetic energy. And as it falls, that motion is the kinetic energy of the ball falling to the ground. Potential energy is equal to the mass times the force of gravity times the height it is up off of the ground. Whereas kinetic energy is 1/2 times the mass times the velocity squared of the object. So how quickly it's moving. But potential energy can also, I mean, it's more than just things falling, right? Another one is thinking about the potential energy of a spring. When you compress a spring, there's potential energy. And it's really the spring constant times the compression squared. And so we have a couple different versions of potential energy that we typically think about when we're looking at things from a mechanical perspective. But now I'd like to focus in on how we're going to think about this in terms of chemistry, right? Because in our labs, we're not going to be compressing springs or sliding things down hills. That's for physics. We're going to think about molecules. Instead. And so we are going to think about chemical energy. So we still have the energy of motion. Kinetic energy for molecules is how they move. And sometimes they're going to vibrate, and sometimes they're going to rotate, and sometimes they're going to just like move around the room, right? But the potential energy piece is going to be stored in the bonds that form within a molecule between our elements. And so chemical energy is really associated with the position of our nucleus and our electrons relative to one another. And so the closer an electron is to a nucleus, we'll see it has a lower potential energy. And the further away they are, the higher potential energy it will have. Remember, an electron and a nucleus are oppositely charged, and so they're going to be attracted to each other. This is similar to Coulomb's law, which we'll talk about more later. But that opposite charge attraction, that is a force. And so when they're closer together, that's a positive interaction than when you have to pull them further apart. kind of like it takes more energy, right, for you to pull apart two magnets. And so when you have them further apart, but they're pulling on one another, that's your higher potential energy situation. And when they're closer together, it's lower potential energy. And so we'll see that our molecules have different amounts of potential energy than others. And the ones that have higher potential energies will be associated with molecules that have weaker and less stable bonds. And ones that have lower potential energy will be associated with molecules that have stronger, stable bonds. And when a chemical reaction takes place, the energy stored in those bonds can be released. And so, like, think about a combustion reaction that gives off a lot of heat. So we'll be kind of diving into this chemical energy in this chapter, and it's really interesting. Some other definitions, some things I'd like us all to be on the same page about now is thermal energy. So thermal energy is a type, it's a category of kinetic energy. So under the umbrella of kinetic energy, we have thermal energy. And so that's going to really be the energy associated with the temperature of something. And we see that kinetic energy is, in general, proportional to temperature. We can say that kinetic energy is actually equal to 3/2 of a constant R times temperature. And so we see that when a temperature increases, the kinetic energy of a set of molecules or atoms also increase as their temperature goes up. And what's happening is that temperature increases, the kinetic energy that's increasing is there's more movement. There's more of that vibrating and stretching and rotating and moving around, which is that translational motion. And so we need to like take into account that when we are talking about increasing temperature now, we are talking about increasing the average kinetic energy of everything in that system that's temperature has gone up. Or that kinetic energy is decreasing and things are slowing down as the temperature goes down. So the conservation of energy and energy transfer. The law of conservation of energy says that energy isn't created or destroyed. So that means in a system, if we have a lot of potential energy at the top of a roller coaster, um, we're stopped, we don't have any kinetic energy. As that roller coaster goes down, that potential energy converts into kinetic energy. It transfers. And as it builds up motion, the amount of kinetic energy increases. As it gets lower down, the potential energy decreases until you can imagine being on the ground on this roller coaster and you don't actually have any potential energy. You have a lot of kinetic energy. And so your velocity is going much higher. And then as you go up in the roller coaster, you convert that kinetic energy into potential energy. You slow down, but you're also now higher up off the ground, so you have more potential energy. And so we'll see that that energy flows kind of transfers between kinetic and potential energy, and that happens in chemical reactions too. As our potential energy is released, let's say, we might see an increase if it releases heat, an increase in kinetic energy of the surrounding area. So that energy is transferring as work, right, as force over distance, or it's transferring as heat. And we're going to be talking about both work and heat in the context of chemical reactions. So I'd like to, since we're going to be talking a lot about heat and we're going to be talking a lot about temperature, let's talk about the differences between the two before we really dive into the content of this chapter. So as we said, temperature is proportional to kinetic energy. It's actually proportional to the average kinetic energy of all the objects or particles in that system, because each one can have a different amount of kinetic energy or motion. And we'll just be able to look at the average, right? We take a step back and look at the more macroscopic rather than focusing in on one tiny little molecule. So higher average kinetic energy is going to mean a higher temperature. It means the particles have more motion. They'll be moving faster, they'll be vibrating faster, they'll be spinning faster. Now, heat. Heat is the energy that's transferred between objects. So it's not temperature. Heat and temperature are different. So it's really the flow of energy that's caused by temperature differences. It's going to always go spontaneously from something warm to something cold. Um, when you hold a hot cup of coffee or hot chocolate or tea in your hand, the heat from that hot liquid warms up your hands. That's why it's so nice to hold a hot cup of something on a cold day. And that heat is transferring from the hotter object, the hot liquid, to the colder object, your freezing cold hand. And it does that spontaneously until the two come to the same temperature. And so that same temperature, when your coffee or your tea or your hot cocoa has cooled down and is now room temperature, and your hands have too, like, so when they're both at the same temperature, it's not as much fun to hold. That's when you've reached something called thermal equilibrium. And so thermal equilibrium is going to be when the temperature is the same of the two, of where the heat was flowing between the two. So heat is that flow of energy, but the temperature will mark that progression of how heat is flowing, as we see the hot object's temperature decrease and the colder object's temperature increase. So we'll use these hand in hand. Another kind of set of definitions to set up before we get started and going deeper is the difference between a system and the surroundings. And so we're going to continue with this coffee cup analogy for a little bit longer, and now we're going to try to translate it into a chemical reaction. So a system is going to be the material or the process we're studying the energy changes within. So if I have a cup of coffee that's hot, it might be my system, right? I've got a hot cup of coffee, and my hand that holds it is going to be the surroundings around it. And so the heat of the hotter object inside the coffee transfers spontaneously to my colder hand. So heat transfers from the system of the coffee to the surroundings. Now, and so heat would be lost from the system to the surroundings. If we were studying the hand and we just defined that as our system, we would then see that heat was taken on by the system by the surrounding hot coffee surrounding the hand. But I think that's a little less intuitive because the hand is actually surrounding the cup of coffee. So if we're talking about a chemical reaction, like, what is the system and what is the surrounding? So the system is the coffee in this example, is going to be the chemical reaction. So the system is what you're studying. It's the change that's taking place between two chemicals coming together and forming some products, right? Through some sort of transformation. So that would be our system. And then the surroundings will be anything else that's not participating in the chemical reaction, but that is around those molecules. So oftentimes, if this is happening in a solution, it's the solvent. It's not participating in the reaction, but it's completely surrounding the molecules that are participating in the reaction. So your surroundings then is the solvent. And then it's probably also that beaker that's containing the chemical reaction, right? So that can also absorb or donate heat into the system of the chemical reaction. And then you could also say, well, it's also to some lesser degree the air around the beaker, and you can kind of keep going. So it's just going to be that space or whatever objects or molecules are there that are exchanging energy with the system that you're studying. So it's the anything that can exchange energy with what you're looking at. All right, we also have some units of energy. Since we're talking about energy now, we need to have a way of quantifying it. And so here are the units that we will use for energy in this class typically. Joules is a very common one that we'll measure energy in. And a joule is really 1 kilogram times a meter squared divided by a second squared. So that's that velocity squared, right? We talk about energy in terms of joules in chemistry more often than not, but a more familiar term might be calories, and we use this sometimes in chemistry. But a calorie is just another unit of measurement for energy, and 1 calorie is equal to 4.184 joules. This is not the calorie that is printed on the back of a candy bar or a snack, or that you look up for what an apple is, right? A calorie that you think about, a nutritional calorie, is still a measure of energy. Like, that's completely the same, but it's really a kilocalorie. So this is a nutritional calorie is really 1 kilocalorie. And this is just the metric system again. Kilo means 1,000, right? So it's 1,000 calories. And the difference that you see when you're looking at this, like on the back of a snack to see how many calories it is that they always capitalize the C. And that is the way of communicating that it's a kilocalorie, which is a terrible way to communicate something about a unit. But I think this is a marketing perspective on considering nutritional content of food and how much energy we can derive from it. That calorie as a kilocalorie is an easier sell than something that's a larger number for actual calories with a lowercase c. So I'll always write nutritional calorie if I'm talking about kilocalories, or I'll say kilocalorie. I'll never rely on a capital and a lowercase c just to differentiate between 1 calorie and 1,000 calories. Another common unit of energy that we see would be on our energy bills, and that would be kilowatt hours, or when we're talking about solar versus like fossil fuel energy. So kilowatt hours is another measure, and it's equal to 3.6 times 10 to the 6 joules. So a kilowatt hour as a measure of energy is a much larger magnitude of energy than just a calorie or just a joule. And so we'll be able to use these with dimensional analysis to convert between them. And I'd like you to be comfortable with those types of conversions for this chapter.